Now, another word that we need is two events being independent. So you probably use the word independent in everyday speech. When you're thinking about this statistically, then what that means is that knowing that one event has occurred does not change your assessment of the probability that the other event has occurred. So I want you to think of two things that really have nothing to do with each other. And even something like flipping a coin. When you flip a coin, you get an outcome. When you flip the coin again, that coin has no memory. It does not remember what happened last time. It may come up heads, it may come up tails. So knowing that the first coin was heads doesn't tell you anything about the probability of the next flip also being heads. But let's think about two things that would not be independent. And so two events are dependent when knowing that one of the events has occurred changes your assessment. The probability of snow. It makes a difference if it's July or January. If I know that it's July, then the probability of snow is going to go way, way down, as long as I'm in the northern hemisphere. Now, if it's January, then the probability of it snowing is going to go up. So the events, season and snow, are going to be dependent because they will depend on the other outcome. But when you have independent events, the probability that both will occur, so probability E and F, can be simply found by multiplying the probability of E times the probability, times the probability of F. So it's a simple way for mutually exclusive events to get the or and independent events to get the and. But you have to make sure that you really do have a mutually exclusive or an independent event before you go to these formulas. If we take a look at example 5.9, we have a satellite that has a main power system and a backup power system. So the probability of failure during the 10-year lifetime of the satellite is 0.05 for the main power system and 0.08 for the backup system. So here, the two events, the main system fails or the backup fails, both of those we'll be able to assume that they're independent. That's kind of an iffy assumption because, there's all sorts of reasons that one could fail that could maybe affect the other. But for the most part, these two events are working, or these two systems are working independently of each other. So we'll go ahead and assume that they are independent. So what's the probability that both systems will fail? Since these are independent events, the probability of both, that's an and, I simply have to take the probability of the main failing and multiply times the probability of the backup failing. And I'm given those values, 0.05, 0.08, and then when you multiply two really small numbers, you're going to get an even smaller number. So this is 0.004. So it is possible that both power systems will fail and then the satellite's going to be in trouble. But it's not very likely. It's 4 times out of 1,000. Now, the probability of M or B. Now this one we have to be a little careful because these are not mutually exclusive. The main system can fail, the backup system can fail. So they can both happen at the same time. So how is that going to affect how we calculate the probability of the or question? Well, it would be helpful here to use a table. If it's not mutually exclusive, then you're going to have to use a table. So I'm going to draw my table. So I have 1,000 and I'm going to have a main fail and then a main not fail, and then the backup fail and the backup not fail, and then we have our totals. We just figured out the probability of both failing. And so we can put that in this first little box. Oh, these are hypothetical tables. So, and this is an example of why we need to go all the way to the 1,000. So here we have 4 out of these 1,000 occurrences that would lead to both systems failing. What else do we know here? Well, we know the probability of B failing. We know that it fails 8% of the time. So B would fail 80 times out of that 1,000. 4 of those times the main system also failed, but the other 76, the main system was fine. We also know that there's a 5% chance of the main system failing, and so that tells us that 50 times the main will fail. 4 of those, the backup will also fail. The other 46, the backup won't fail. And that allows us to figure out the rest of this. We take 1,000 and we subtract 80, and we get 920 in that spot. And then take 920 and subtract 46. We get 874 in that spot, and we get 950 for this last total. So we had to do a little extra work for this one because these were not mutually exclusive events. Now we can look at the events here. M, so that's the 4, the 46, and then B, that's the additional 76. So what's the probability that either one will fail? So we'll add 4 plus 46 plus 76 and divide by 1,000. We get 126 over 1,000, and that simplifies to 0.126. Now, what about the probability that at least one system works? Well, here, the only time that at least one system works is not true is when both have failed. So this actually is the opposite of 1 minus both fail. And you can easily get this by doing 1 minus 0.004, and we get 0.996. But you also could have done this in the table, because at least one system works means that either B did not fail, which is the 46 and the 700 or the 874, or M did not fail, which also adds that 76. When you add all of those up, you get 996 out of 1,000, which is 0.996. And then the last question, what's the probability that the main system fails, but the backup system did not fail? Where is that in this table? Where do I see a main failure, but a backup not failure? And that's right here with these 46. So that's 46 out of 1,000, and that is 0.046.